A rational function is just a function that has a fraction involving variables in it. And so the key is we have to have a variable in the denominator, like we have in both of these examples. In the first one, we don't have a variable in the numerator. On the second one, we do, but that doesn't matter. What matters is that we have a variable in the denominator. Now, the most basic rational function is the one that we see here, f of x equals 1 over x. So we want to generate what the graph of this looks like so that we can use it as a building block for other more complicated graphs that have some other elements occurring in the function, like what we see in the two examples at the very top. So it might be useful for us to make a t-table to help generate some xy coordinates to start to get a feel for what this graph looks like. So if we start off and we plug in 1 for x, we're going to get an output of 1. 1 divided by 1 is just 1. So we can go ahead and put a dot on our graph there at 1, 1. If we plug in 2 for x, 1 over 2 means our output is 1/2. So that means our output is right about there. If we plug in 3 for x, hopefully we're starting to pick up on the trend, we end up with 1/3, an even smaller number. Or in other words, as we go farther and farther out to the right, as we plug in larger and larger numbers for x, we're going to get values for y that are smaller and smaller, but we're never going to quite get to 0. And we can see this if we were to say plug in 100 for x. We would get 1 over 100 as our output. So a very, very small number, but we'd never end up going negative. We'd never end up hitting 0. So as a result, from this point here, our graph is going to get closer and closer to the x-axis, meaning that the x-axis is going to serve as an asymptote, a line that the graph approaches but doesn't cross. But what happens if we continue with the t-table and we inch closer to the y-axis? So for example, if I try to plug in 0 for x, I run into a problem because I get 1 over 0, and we know we're not allowed to divide by 0, so that's undefined. So I'm not allowed to plug in 0. But what happens if I plug in something pretty close to that? So let's say we plug in 1/2 for x. Well, 1 divided by 1/2, I can rewrite that as 1 times the reciprocal. So instead of dividing by 1/2, we can multiply by 2 over 1, so we get an output of 2. Or if we plug in 1/3 for x, so plug in something a little bit smaller, I've got 1 over 1/3, and so that means I've got 1 times 3 over 1 if I rewrite it as multiplication, so I get an output of 3. Or in other words, as I get closer and closer to the x-axis, if I plug in 1/2, I've got 2. If I get a little bit closer, I get an output of 3. Or in other words, my graph is shooting upwards as I get smaller and smaller inputs, inputs that are closer and closer to 0. So we have this shape of this graph where as we go farther and farther out to the right, we're approaching the x-axis, but as we get smaller and smaller inputs, approaching 0, our graph shoots up to positive infinity. And so again, we have another asymptote, but this time it's vertical, that's running along the y-axis, a line that the graph approaches and cannot cross. Now what happens if we plug in negative numbers for x? So if we change some of these up, let's say we plugged in -1 for x. Well, our output would then just be -1. 1 divided by -1 would be -1. So we'd have a point here. If we plugged in -2 for x, we'd generate -1/2 as an output. If we plug in -3 for x, we'd just get -1/3. So we'd kind of get the same thing happening over here, just from below. So our graph would be approaching the x-axis the farther out we would go. So we've again confirming that the x-axis is serving as this asymptote, the line that the graph approaches but does not cross. And the same thing is going to be true here. So I still can't plug in 0, but if I plug in -1/2, I get -2 out as an output. If I plug in -1/3, I get -3 out as an output. And so that means I'm going to end up with a graph that is shooting downwards like this. So I end up with these two branches that are kind of bounded by these asymptotes. I have a vertical asymptote in this example that's running along the y-axis, and I have a horizontal asymptote that's running along the x-axis. And so I end up with these two branches, one over here on this side of the y-axis, and then one over here on the other. And so most of our rational functions are going to have shapes along these lines, where we have a vertical asymptote located someplace, we have a horizontal asymptote located someplace. We just need to make sure we find those locations, and then we're going to have these two branches on either side of the vertical asymptote. So we'll explore that more in some future examples. But before we get to some more examples, let's take a look at some rules as to how we can determine where these asymptotes are located to then use those to help build our graph. So first of all, vertical asymptotes, the vertical line, for example, like we had along the y-axis that divided our graph into two separate parts on the left and the right, vertical asymptotes occur at the zeros of the denominator. So basically what we can do is we can set the denominator equal to 0, solve for x, and whatever we get, that's going to be the location of a vertical asymptote. So in the example that we did where the function was y equals 1 over x, if we just take that denominator and set it equal to 0, then that is going to give us the vertical asymptote. If we had something more complicated in the denominator, then we would just have to solve for x, as we'll see in some other examples in a minute. For the horizontal asymptotes, that's a little bit more complicated. So the horizontal asymptote is going to be the x-axis. It's going to be y equals 0 if the denominator has a higher degree, meaning a higher exponent than the numerator. So in the example here, there's no x in the numerator, so we'd say the degree is 0. The exponent on the x in the denominator is 1, so the denominator has the higher degree, it has the higher exponent, and so therefore y equals 0, the x-axis, is going to serve as our horizontal asymptote in that circumstance. If the numerator and denominator have the same highest exponent, so let's say we had x plus 2 over x minus 6 was our function. So now we have the same highest exponent on both the top and the bottom. So in this circumstance, the horizontal asymptote is going to be the ratio of the leading coefficients, meaning it's going to be the ratio of the coefficients, the numbers that are in front of those highest exponent pieces. So in this case, the coefficient in front of the x's is 1 both times, so therefore our horizontal asymptote would be y equals 1 over 1, which would just be 1. So instead of having the horizontal asymptote running along the x-axis, it would be at y equals 1, just 1 unit up. If our function was something along the lines of 2x minus 1 over x plus 2, if that was our function. Well, now again, we have the same highest exponent on both the top and the bottom, so now our horizontal asymptote would be the ratio of these leading coefficients. Well, the coefficient in front of the x is 2 in the top, it's 1 in the bottom, so our horizontal asymptote would be 2 over 1, or y equals 2. So instead of having a horizontal asymptote on the x-axis like we had on the 1 over x example, now it would be at the line y equals 2. And then the other couple features that we're interested in when it comes to these graphs are where the graph may cross through the x and y axes. We don't always have intercepts along the x and y axes, but if the graph does have them, we want to make sure that we find those. And so the x-intercept occurs when at any number that makes the numerator equal 0. So basically what we're going to do is we're going to take the numerator, set it equal to 0, solve for x, and if we can do that, if we can solve for x, if there is an x in the numerator, then whatever value makes the numerator equal 0, that's going to be the place where the graph crosses through the x-axis. And then the y-intercept is going to be the location where the graph crosses through the y-axis, and we find that by just plugging in 0 for x. So we're going to go through all of these kind of ideas in the next couple of examples and use the vertical asymptotes, the horizontal asymptotes, and any intercepts that the graph might have to generate the graph of these rational functions.